In the last video, we finished chapter 3 and went over question 2 of homework 3. I realized that there seems to be some technical issues, with the video. Uh, some of my screen, it's gets cut smaller, and sometimes when I write, the writings are not showing immediately. So um, I have no idea what's the reason for that. Hopefully, it won't appear in this video. In From now, we're going to study a new chapter, chapter 4, called risk measures. For this chapter, I prepared my own lecture slides. That's because I feel there's a little bit more I can offer from my own version than the standard textbook slides. Obviously, this is a very important topic, risk measures. It's not only important for actuarial science, but also for quantitative finance. Of course, here in this course, we mainly focus on two specific risk measures, value at risk and conditional value at risk. Of course, there are many, many more generalizations based on these two popular measures. First, here we have some standard references. Obviously, 5 is our textbook. The standard reading is actually book 4. It's a very, very comprehensive textbook on risk management, written by some of the well-known experts, especially Paul Ampers. He's one of the most cited scholars in risk management. And of course, there are several papers. This one is likely the most classical paper, at least from a mathematical point of view. It was published in Mathematical Finance in 1999. I think it has already generated citations over, I can't remember the number. I think now maybe 8,000 or even more than that. That is a surprisingly high number for a mathematical finance paper, okay? The next one, the 2002 paper by Hans Former and Alexander Schitt, they did a very important generalization from coherent to convex. It's also considered another big improvement in the field. This is the book written by them. It's a very deep textbook at the PhD level. So if you want to challenge yourself, you can read their book. So here is a quick outline. I think in this video, I will do section 1, section 2, basically lay down the foundation of risk measures. Section 3, it's optional. It's a mathematical concept which helps us to formulate things in a nicer way. 4 and 5 are the most important sections of this chapter. In the final section, we will talk about a few generalizations, right? So here, VAR and TVAR, or sometimes I actually call it conditional value at risk. Those two are special cases of transformed risk measures, okay? A quick question is, what is risk, right? Why do we need risk measures? Here I copied a definition from Wikipedia. Risk is the possibility of losing something of value. I think this is a very good definition, right? So it's a probability of something. So it does not mean you will lose something of value for sure. It's only on the probability level. So that's why sometimes people get confused between risk and uncertainty or randomness, right? So the other, uncertainty also means something might happen, but without sureness, right? So, but here risk means on top of uncertainty, you will lose something for sure, right? In some language, uncertainty does not necessarily mean a bad thing. It just means we are not sure, which one will happen. Like let's say we talk about weather. Oh wow, the temperature may be between 50 degrees and 60 degrees. Right? It's uncertain in the sense that at this moment we don't know the temperature at, let's say, 9 a.m. tomorrow. We don't know, so it's uncertain. It's, let's say we have a prediction. It's between um, 50 and 60. So it's something between those two values. It's uncertain, but to us there's no risk, right? If it's 50, it's okay. If it's 60, it's probably also okay for us, right? We don't lose anything, in that sense. So it's only uncertainty, but it's not a risk to us. Okay. Of course, you can embody this uncertain information into risk. Let's say you are doing something, and what you are doing depends on the temperature, right? And if temperature is higher, okay, it's safer, right? Maybe temperature drops below something, it's no longer safe to perform the activities you intend to do. Then there is a risk, right? Uh, the reason why we need risk measures is simple, right? Because we want to quantify, right? Only when you can quantify, you can somehow come up with scientific methods to manage the risk or to minimize the risk, right? To us, like to people in the actuarial science, there are so many examples, right? We want to buy reliable insurance policies, health insurance, home insurance, auto insurance, property insurance, all kinds of insurance to minimize risk, right? So that's why the reason why we need risk measures is very straightforward, right? So we like to quantify risk so that we can somehow come up with a solution, right? Either we buy insurance policies, or we somehow avoid doing certain things that results in a big risk. So in Markover's framework, mean variance framework, that is a breakthrough in modern portfolio theory, the risk measure is nothing but the variance. This is not new, right? To us, variance it's something we all know, right? From the first course in statistics. So here the idea is very simple. Given two trading strategies with the same expected return, the one with smaller variance is preferred, right? So in that sense, we are trying to minimize risk. Okay, of course, in that case, risk is the variance of the portfolio return. Right? We're trying to minimize risk. But here we have a question. Is variance an ideal risk measure? Right? Of course, we can think of many drawbacks of variance. Right? So let's say still in this investment example, you are trying to make profits, right? But if we use variance, we may penalize good performance, right? So variance only measures the fluctuation from the mean. It could be good fluctuation. Let's say you are, so this is the baseline, so this is the mean. So it could be, right? So let's say there may be a few scenarios that you get outstanding return, and there are many possibilities you will lose some money. In this case, the variance might be huge because you have a few outliers, that give you a large fluctuation from the mean. But to us, those are the good signals, right? They are very uncertain, right? The distance from the mean is huge, but they are in the good distance, right? But of course, it is also possible that you have negative fluctuations in a big value. That is bad, right? But variance penalizes both, at the same level, and that is something probably we don't like, right? So that's why some people they are trying to promote semi-variance. So if you are on the investment side, you are trying to only penalize the negative deviation, not the positive ones. Okay. With that in mind, we have many different types of risk. Okay. Take a quick read. Okay. These concepts are important in finance, but relatively speaking, not that important to us, at least in this course. So I leave that to you to read. Now let's start with the basic definition. Okay, let's say you can pretty much ignore everything down here. Okay, that's fine. This is the most important mathematical definition for risk measure. A risk measure is a real function denoted by rho that maps from some set of risks to a real number. So basically, the idea in the mathematical viewpoint is very, very simple. A risk measure is a function, or it's a functional, if you want to call. It maps from a random variable because risk is a random variable. So X is a random variable. So basically what it does is to assign a value for each risk. So basically it's assign a value, a real value to a risk X. Okay, here we are mainly interested in random variables, right? So of course, constant is a trivial case of a random variable, but what we are not interested in the trivial case. So this fancy calligraphy X denotes the set of all the random variables we consider. Okay. Here we have some quick examples. First, I mentioned that in general, the risk measure does not need to be a positive number. So it's okay to assign a negative number to a risk. Okay, that is because the value itself is not that important because we can always scale. If rho is a risk measure, we can times it by a constant. So C times rho is another risk measure, and we can pick this C to be as large as you prefer. So the value itself doesn't matter. So it's the relative value that value matters to us. Again, let's use a financial example to demonstrate this. Let's say you have an investment opportunity and you plug in some risk measure that gives you a value. Immediately, what you want to do is to compare this to a relatively safe investment. Let's say so let's say this is the baseline. So this is saving account. Let's say gives you 1%. Well, 1% now is outstanding, given that the interest rate is pretty much zero. So let's say you can put money in a saving account that gives you 1% return over, let's say, over 1 year. Okay, so you can plug in your risk measure. This will give you a value, right? You can think this as a benchmark, and then you compare whatever the risky opportunity you have, right? You compare this with rho of X. Then you get a better idea how risky your position is, right? Because we think saving account is very safe, right? So there's no risk of default. 1% return is guaranteed. And if you get something which is very, very big, comparing to rho of XB, then you will think this opportunity is very risky, right? So the understanding from this example is it's obvious, right? So I'm trying to emphasize that the value itself, rho of X, is not that important. You always compare this to some of your benchmark. Here I put saving account as a benchmark. You can try like SP 500, like index as a benchmark, or anything you want, right? So let's say we can compare to Dow Jones, industrial index as well. So basically, we want some kind of benchmark. The same, in the insurance, in the insurance rate making, we also have some preferred customers. Right? For instance, those when you apply for auto insurance, they will ask for your age. Right? So if you are young, you are somehow considered to be more risky than those married couple in between 30s and earlier 50s, right? Those are the benchmark. So there will always be some benchmark, and then you do comparison with this benchmark, and then the companies will get a better idea of how risky, your business is to them. Okay. Here I give you some naive examples. Expectation, you can think it as a risk measure. Right? Especially this helps when you do when you study investment example, when you are in the investment world. In that case, of course, you can put a negative sign if you want. Okay, variance we already talked about, and then immediate consequence of variance is we can also apply standard deviation. Right, they are close, but they are not the same. Okay, we will see that they are not the same. Variance and standard deviation, they are not the same risk measures. They have different properties. But what would be the desirable with properties a risk measure should have? So let's say X denotes one risk, Y denotes another one. What would you expect on the relation if the risk of Y is always bigger than the risk of X, right? Then naturally you would expect this, or you would hope this to happen, right? So if the size of Y is always bigger than the size of X, let's say those are losses. Excuse me, I should do the opposite, right? Because to us, we usually treat X as loss, right? I'm from the mass finance side, so to me, I usually use X to denote wealth or denote return. So here, since we are in the risk management side, we want to use random variables to denote losses. So if what is so if the loss, the original one is actually correct. If the loss is bigger, then the risk should be bigger, right? So that's our intuition, right? What would be this? If the size of the loss is increased or decreased by a constant, what do you expect, right? So those are the questions we are trying to answer, and then we motivate. Those motivate us to come up with some standard axioms we'd like to propose. So let me give you the definition, or let me give you the introduction of this, and then we will discuss one by one. First, we define monetary risk measures. But to define this type of risk measures, we need two axioms. The first one is monotonicity, which we just mentioned. So if some loss is always bigger, the size of this loss or the measurement of this risk should be bigger than the measurement of a smaller risk. This is what we refer to as monotonicity. Later on, we will simply call this axiom M. M stands for monotonicity. This makes intuitive sense, right? A bigger risk should be measured in a bigger amount, right? The next one is called the translation invariance, and we use notation TI. Again, it stands for translation invariance. Those are the initial letters of these two words. Given any risk measure low and a constant M, we have this. So what is the understanding behind this? Let's say you are let's say central bank or regulator. So when you measure risk, after you measure risk, okay, this is a number, right? So let's say X is the risk of an insurance company, and you are a regulator. So you apply some kind of risk measure to a company, and you get a number. you can think that number as some kind of deposit. So an insurance company should deposit this amount of money with you so that you are somehow can guarantee its customers will always get paid if they file for a claim, because to have a steady society, we don't want insurance companies to go bankrupt, right? That's why during the financial crisis, the federal bank or the federal government bailed out AIG, right? One of the largest insurance companies in this country. You don't want an insurance company to go bankrupt, right? Because there are millions of households who depend on insurance companies to cover their claims, right? Like say healthcare, right? I mean, hardly anybody can really afford the crazy amount of healthcare, by themselves. They rely on insurance companies to pay for the claims, right? So if an insurance company goes bankrupt, if they can't cover your health bills, that could be a disastrous event, right? It could cause a lot of bad consequences. So that's why you can think this as an amount that the insurance company should reserve. Okay, now under that context, if the risk goes up from x to x plus m, and m is a fixed constant, okay? Previously, you only required the company to deposit low of x. Now, given that the risk will go up by m, so let's say m is a positive constant, so it go up, so the risk will go up by m. All you need to do is to ask the company to deposit extra m dollars. Then all the additional risk will be covered by this fixed amount. So you go back to the previous case, right? If the previous risk measure is appropriate, right? So if it works in the past and now the future size of the risk will go up by a fixed amount, you just need to charge exactly the previous one plus this extra amount. Then your regulatory policy will still be appropriate, right? So that is the interpretation of translation invariance. Okay. Sometimes people also call this cash invariance, right? So this again, cash invariance probably fits better with the example I just gave you, right? Because here we interpret low of x as some kind of cash reserve. If the size of the risk goes up by m, the cash reserve should go up by m, right? Of course, if m is negative, the risk is reduced by m. The company can reduce the reserve by m as well. So it's you can think this as kind of a nice property, right? Again, I think it's in some sense, translation invariance makes sense, right? According to the example I gave you. One implicit assumption is that we somehow normalize the interest rate to zero. So because when we talk about reserve is placed at time zero, and the risk is realized at time t. So let's say we consider auto insurance for 6 months, and we assume all the claims are paid at the end of 6 months. But your reserve should be reserved at time zero, right? So you deposit some money at time zero and use this to pay the claims 6 months later, right? So here, by cash invariance, we ignore interest rate. Okay. So given those two axioms, we can easily define monetary risk measure. A monetary risk measure is nothing but a function low that satisfies those two axioms. So that is the definition of monetary risk measure. For instance, expectation is a monetary risk measure because it satisfies those conditions, right? So if you have x if you have two random variables, x and y, x less than y, the expectation of x obviously is less than the expectation of y. And when you take expectation, constant can take out. So expectation is a trivial example of monetary risk measure. Right? A nice thing from the translation invariance is that we have this. We can take a special value for m, and we take m to be negative rho of x. Right? Again, rho is a risk measure, so rho of x is a real number. Negative rho of x is also a real number. So we apply this for m, you get this is 0. Right? Of course, 0 itself doesn't mean anything, but you can normalize it, like in the next axiom. We normalize 0 to 0. If you don't do anything, if there's 0 means there's no loss. Of course, there's no gain as well. So if you do nothing, so that means no action will give you 0 risk or 0 measurement of risk. So this serves as a baseline. Right? In this case, as you can see, 0 means no risk because the company does not involve in any business. Right? The x is 0 means no return, no loss, nothing. Right? Just a no business. This you can think as a baseline case. Right? If the company is not involved in any business, the risk is 0. Okay. So from here, what you can think of is if it is involved in some kind of risky business as measured by X, the company can reserve exactly this amount, rho of X, to eliminate the risk. Okay, so here eliminate means from the risk measure point of view. Okay, not eliminate all the losses. Okay. From there, we also have this nice equality, but I mentioned here in this remark, it's not required to normalize the risk at 0 to be 0, but somehow, it's convenient, right? For instance, E of 0 is 0, right? So it is normalized, but we can apply a constant to it as well. So we can apply, let's say some constant, right? In this definition, this is also a monetary risk measure, but as long as your C is not 0, this is not normalized, right? So normalization is not a requirement, it's rather a convenience that we usually assume, okay? Lemma 1 is a technical condition. It means, so we can ignore, that's not important. Now let's move a little further. We add one more axiom, that is convexity. So first, let's define what is convex or convexity axiom. Let rho be a risk measure. Okay, let x and y be two arbitrary risks. We have this. By the way, this is the definition of convex function. This is how we define convex function. Okay, the aggregate of the risk of the aggregate less than the aggregate of risk. So that's the mathematical interpolation. But we do have the financial meaning that is called the diversification. Okay, let's say you have a risk. By diversify means by converging them, by merging those two risks together, you are likely to reduce the risk. Okay, this gives us some motivation for diversification in portfolio management and merging in business operation, because you can think this. So X is one business line, Y is another business line. So if you leave them as independent, the risk is bigger than the risk of merging those two business lines together. So again, that's the concept of diversification, right? In finance, in portfolio management, that is a fundamental idea or the foundation for diversification, right? We don't just invest in one stock. we invest in many stocks, hoping that the diversification can reduce risk. So that is the rationale behind this convexity axiom. That's because we normally believe that diversification helps reduce risk. So that's why if it helps reduce risk, the risk measure should be smaller, less than or equal to the undiversified, right? So that is the economic interpretation of this. A risk measure is a convex risk measure if it satisfies three axioms: monotonicity, translation invariance, and convexity. Okay, if rho is normalized, if rho x equals zero, we have this nice property. Okay, sometimes it's some people call this nice properties. Sometimes you may also want to debate why this is the case, right? Here, what I give you is just the mathematical result. Of course, this is a question, right? Does diversification reduce risk? Like sometimes it does, sometimes it doesn't. That's why there are some criticism on the convexity axiom. Finally, we add another axiom. It's called the positive homogeneity. Again, this is, well, first, mathematically, it's very convenient, right? That means a constant lambda can be factored out, and it's a positive constant. How do we understand this? Let's use two examples. In the first example, we use a stock trading. Let's say when you trade one share of stock, we use X to denote the risk. So let's say X is the loss from trading one share of a stock. If you trade two shares, positive homogeneity means it's double the risk of trading one share. So from that sense, it's reasonable, right? The risk of trading two shares of stock is double the risk of trading one share of stock. Okay, now let's use insurance example. Let's say X is the risk of insuring one policy. Okay, then by positive homogeneity, the risk of underwriting two policies is the double of the risk of writing one policy. So in that sense, it's also reasonable, right? But when this lambda is very, very big, you wouldn't necessarily say the risk of selling 1 million policies is 1 millionth the risk of selling one policy, right? Because we do have the diversification concept or a law of large numbers, right? When a company sells 1 million policies, the risk is actually diversified because most of them will not come back with a claim, right? But if you just insure one policy, you might be very, very unlucky, right? That one particular policy may be resulting in a huge claim, right? But if you insure for 1 million policies, you have the averaging effect, so that maybe there are a few very bad policies, but on average, each one is reasonable. You are better, or you are at a much safer ground, to insure 1 million, policies, right? Rather than just use 1 million times the risk of one, right? So for small lambda, maybe it makes perfect sense, but for a huge lambda, it's different, right? The same for the stock trading. If you buy one share, you have zero impact on the price. If you buy two shares, you still have zero impact on the price. So it's reasonable to say the risk of buying two shares is double the risk of buying one share. But if you buy 1 million shares, you're going to impact the price, right? You're going to push up the price. So the risk is actually minimized. But of course, when there is a catastrophic event, you are holding 1 million shares of stock. There's no way you can easily liquidate this large position, right? Then your risk is amplified, right? Not only by 1 million, it's probably more than 1 million, right? So here my point is straightforward. Okay? Sometimes this positive homogeneity makes sense, but not always. Okay, that applies to pretty much all the axioms. Finally, we define coherent risk measure for some function that satisfies all 4 axioms: monotonicity, translation invariance, convexity, and positive homogeneity. We should mention that this axiom, positive homogeneity, actually implies normalization. That's because well, you can take limit, right? If you take limit, the right hand side is 0. So in that sense, you can think that the limit case low 0 equals 0. Of course, you can also apply a different technique to get this to discuss lambda is greater than 1 or less than 1. Denote by X the risk of underwriting one policy, right? So this is the example I just mentioned, right? If n is relatively small, probably we are more likely to agree the axiom pH holds. But when n is very, very big, we probably don't like the idea of axiom positive homogeneity, right? Because we tend to think diversification should kick in. Then the right hand side should be less than the left hand side should be less than the right hand side. So that's why I mentioned risk usually does not grow in a linear way. Okay, in some cases it's not bad to apply a linear approximation, but sometimes it's really really not appropriate. We introduced the 5th axiom. It's called the sub-additivity. Okay, this usually is introduced early on instead of convexity because we have this lemma: positive homogeneity and convexity is equivalent. Given positive homogeneity, convexity and the sub-additivity, they are equivalent. Okay, that is why usually in actuarial science we propose sub-additivity because this makes more intuition. Okay, that fits our direct meaning of merging. Right. This gives you a better understanding of why companies merge. So let's say X is the loss of one company, Y is the loss of another company. On the right-hand side is when they do not merge. Okay, so that is the risk on the right-hand side. If 2 companies merge together, okay, their losses are combined to X plus Y. The risk is smaller, or at least as big as the non-merging case. So this gives you the motivation for, or this gives the explanation for why companies merge, okay, or why you put more than one stock in your portfolio, okay. By this lemma, we can also define coherent as monotonicity, translation invariance, positive homogeneity, and the sub-additivity. Again, this is questionable, from time to time. Here we have a quick example. By the way, this is something we will learn in a different course called insurance premium principle. Here, what we apply is we apply a factor bigger than 1 to the expectation. Okay, we call theta the loading factor. Well, if you take 5, 6, 40, you will learn a little bit more of the premiums. So we can easily check it satisfies monotonicity, positive homogeneity, and sub-additivity. but not translation invariance, right? I mean, this is very easy to prove. Right? Obviously, in general, that does not equal to log x plus m, right? Unless theta is 0, right? Well, in general, we apply a strictly positive theta, so the translation invariance actually fails here. We have more counter examples, right? For instance, so let's say we have variance as the risk measure. Okay, again, translation invariance is violated because if you add a constant to a random variable, the variance is the same. So it does not satisfy the translation invariance. So the variance as a risk measure is not coherent, right? And sometimes we tend to think coherent is a good thing. In fact, if they are positively correlated, you also have this. This violates the sub-additivity because by sub-additivity, we want this to be less than or equal to log of x1 plus log of x2, right? But if two risks are positively correlated, merging them together actually makes a bigger risk in terms of variance. So it also violates the sub-additivity. So by the way, that's why variance is really not a good risk measure, right? However, if we apply standard deviation, similarly, translation invariance also fails, but sub-additivity actually holds. Okay, I leave this for you to prove. This is not complicated, right? Because we know I shouldn't use low because we use low to denote risk measure. That's because correlation coefficient is always less than or equal to 1, right? Use this to prove sub-additivity actually holds for standard deviation. Next, we have something more complicated. Let's say we have this. Okay, and then by the way, for both variance and standard deviation, the monotonicity also fails because we no longer have the monotonicity, right? You can have a very fluctuating risk that is small, but you can have what we have is this in general does not hold. You can come up with many examples, right? Again, that's why variance is really not ideal. Some people propose this semi-variance. Again, it's not a nice risk measure in terms of satisfying axioms, but from the finance point of view, here you only penalize the negative part. So it's the loss part. Here you only penalize loss. You do not penalize gain. So in that sense, it's good. But of course, it's actually very complicated. It's highly nonlinear. It does not satisfy most of the axioms we propose. So we do not consider it here. Let me stop here for this video, and we will continue.